I'm happy to introduce Chris Chen, who's coming from the West Coast to tell us that the quantum Fourier transform, as it turns out, as of the paper last week, is low entanglement. So thank you, Chris.
Okay, hi everyone. I'm Chris, and I'm a first-year graduate student at Caltech. And this work is in collaboration with Miles Stoudemire, who's a co-organizer of this event, and Stephen R. White from UC Irvine. And this work was mainly done when I was an undergrad at UC Irvine. So I will start to give with an overview. The quantum Fourier transform is one of the most important ingredients in quantum algorithms. However, we'll actually show that the core part of the quantum Fourier transform can only generate small entanglement on qubits. So we can then simulate the QFT in classical machines using tensor networks, demonstrating a super fast Fourier transform on restricted classes of functions. That means this is like faster than fast Fourier transform for certain classes of functions. But it turns out there can be a lot of these kind of functions. So note this actually does not mean that the QFT can be simulated classically for arbitrary inputs. I will actually explain why. So this is the outline of my talk. I'll start with the introduction to the QFT and the QFT tensor network. So I'll just show this. So the first two sections will be sort of the setup of the talk. And the next three sections I will use the setup to sort of analyze the structure of quantum Fourier transform and demonstrate the small entanglement. And the last two parts will be the classical simulations of the QFT. So the QFT has been widely used in quantum algorithms for provable advantages over their classical counterparts. For example, the most famous one is the Shor's algorithm for factoring integers. And there are also hidden subgroup problems, phase estimation, simulating quantum dynamics, quantum arithmetics, solving linear systems of equations, and so on. So the QFT's power actually stems from its ability to find periodic structures of quantum states, which many quantum algorithms turned out to rely on to gain a provable advantage. So the QFT is basically the discrete Fourier transform over the Hilbert space spanned by n qubits. So in terms of matrix, you can either express as this Cad and Bra notation, or you can express this as a big matrix on the Hilbert space spanned by the qubits. So here, this Q is a shorthand notation for the binary digits represented by the qubits. So this might be confusing because this is not a product of the qubits. It's actually means sort of like put the digits as like a chain of like base string. And here, the omega is just a phase generated by the sort of like this number of qubits, right? So the QFT actually has a product form representation. That is, we can represent it as transforming a input base string into a product state in the Fourier basis. So basically transform a qubit string Q1 into a superposition of 0, 1 with a relative phase depending on the nth digits. And the second qubit will be transformed into these states with the phase depending on the n-1 qubit and nth qubits. This 0 point Q1 dot Qn is the shorthand notation for this number. So it's like it's kind of like 0.315 or something, except it's represented as binary digits. So to implement the circuit for QFT, here I use the Fn. One usually considers the decomposition. So basically, we consider it as two parts. So the first part, I call it Qn. So it's pretty much the same with Fn, except we sort of swap the first qubit with the last qubit and swap the second qubit with the second to the last qubit and so on. And this Rn is like a bit reverse operator, which swap everything back to match the order. So we consider such decomposition really because the circuits for Qn can be derived directly from the recursive structure of the discrete Fourier transform. So for example, the 4-qubit QFT circuit will look this, where you can see here, there's some kind of recursive structure in this Qn, and then we sort of add a big bit reversal gate in the end to sort of like swap the order back. And this H gates are defined as this. Basically, they are hard mark gates, and this P gates are phase gates. And this dot here basically means the control, like if the first qubit is 1, it applies the phase gate, but if the first qubit is 0, then it applies just identity. So one may actually realize that bit reversal operator is actually not needed to perform the QFT on a quantum computer, because one can just track the bit order classically. So generally, whether one wants to use, the bit, the one with the correct bit order or the reverse bit order, kind of depends on the qubit architecture. For example, how our qubits are connected together. So in general, there's not really a benefit of using one over the other. So at the core, both other operators are not very different. However, it turns out their entanglement structure actually differ a lot. So with this Fn having maximal entanglement, while Qn has a very small entanglement, which will be shown in our work. Okay, so from now on, I will actually refer Qn like the one without bit reversal as the QFT, and Fn as the discrete Fourier transform. Okay, now I'll introduce a tensor network representation of the quantum Fourier transform. So while the quantum circuits of QFT is technically already a tensor network, it consists of this like long-range controlled phase gates. So can we represent them elegantly as a contraction of local tensors? So I sort of like highlight the elegantly because one can sort of argue that this crossing between two lines is just two identities. So it's also a local tensor, but it's kind of like it's kind of redundant here. So we want to sort of simplify the tensor network structure as much as possible. So only local tensors are present. So we can actually decompose the controlled phase gate, include two phase, but a controlled phase gate as a contraction of 2 order 3 tensors. So in order to see how we sort of express this controlled phase gate as the sum of 2 operators, where 0 is the projector to the 0 space, and 1 is projected to the 1 space. And we can sort of see the sum can be actually decomposed into a product of 2 operator valued vectors. So that sort of means like we cut the line in the middle, and then we get like 2 order 3 tensors contracted together. So this notation here basically means for operator valued vectors, we sort of like tensor product match the elements. So we call the tensor at the top an order 3 copy tensor, and the tensor at the bottom an order 3 phase tensor. So their tensor elements are defined like this. Basically, this delta is the Dirac delta. It only evaluates to 1 when all the subscripts are matched, like either they all take value of 0 or they all take value of 1. So for this phase tensor, you can sort of see it's basically kind of similar to the copy tensor, except like you only have constrain the horizontal indices to be the same, and you add like a phase. The product, like a phase, depends on the product of the inputs. So when 2 controlled phase gates are adjacent to each other, we can actually move one of the copy tensors and contract it with the order 3 phase tensor into an order 4 phase tensor. So by moving, as I really just mean like there's you can sort of like this is really just a tensor identity associated with the copy tensors. You can sort of move this dot here across here, and then you can see this one combined together will become sort of a new phase tensor. And this is very similar to the order 3 phase tensor, except like we sort of introduce another line here, and we sort of pass through the x2 like across the tensor in the vertical direction. So therefore, for a series of these controlled phase gates, we can sort of merge them all together into a single matrix product operator. We call it a phase MPO. So For people who don't know about matrix product operators, they're just this contract chain of order 4 tensors with order 3 tensors at the boundary. So then the entire QFT circuit can be represented as a series of these phase MPUs with hardmark gate sandwich between them. So we refer this structure as the QFT tensor network. So in some literature, actually, this is how people draw the QFT circuit is exactly, because this is just like control, like a controlled qubit with multiple phase gates. But here we can actually interpret every sort of tensors locally instead of considering this as like a large controlled gate. Okay. Now I'll introduce about operator Schmidt decomposition. So this is a good metric to quantify the entanglement of an operator. It examines how compressible an operator is and the operator's average power of creating entanglements on some quantum states. So we'll specifically talk about unitary matrix because this is quantum circuit, so everything is unitary. So for a unitary matrix, the operator Schmidt decomposition is in this form, where this chi here is the Schmidt rank, and this sigma k here are Schmidt coefficients. And this AK and BK are operators acting on the two subsystems respectively, and they satisfy this sort of orthogonal property in the operator space. And this big N is just the dimension of the entire system. Notice this is only applied to unitary gates because so for non-unitary gates, this N will depend on the norm of the operator. But for unitary gates, it's just the product of the dimension of two subsystems. And the Schmidt coefficients are normalized here, and we sort of organize them in descending order. So this is actually just equivalent as the singular value decomposition. So by that, I mean, we first reshape the unitary into a matrix in the vertical direction, and we apply singular value decomposition to it. So we get two sort of isometries, and here is a diagonal matrix with singular values on the diagonal. And then we can just express the sum, which is basically breaking these tensors as a sum of different tensors. And this orthogonal property in the operator space is basically just saying this A and B are isometric tensors. So this is pretty natural if we consider singular value decomposition. So with this introduction to the operator Schmidt decomposition, we can now sort of analyze the QFT Schmidt coefficients. So the main theory of our paper is basically we're stating that the Schmidt coefficient of Qn has exponential decay. For that, I mean, by partitioning the Hilbert space of the QFT into subsystem A with qubits 1 to j, and subsystem B with qubit j plus 1 to n, then the Qn has this Schmidt decomposition, where you can see the Schmidt rank is the minimum between 2 to the power of j and 2 to the power of n minus j. And the Schmidt coefficients will satisfy an upper bound of exponentially decay. So the mathematical reason for this exponential decay can be understood through two steps. So the first step is that Schmidt coefficients of Qn are actually equivalent to singular values of the top left submatrix of the discrete Fourier transform matrix, which by that I mean the Fn. And the submatrix of the DFT matrix are actually known to be approximately low rank. So they are extensively studied in another area of signal processing as the spectral concentration problem. So we will go over these two steps one by one. So to understand the first step, we first claim that the following tensor network represents the 2 to the power of n times 2 to the power of L top left submatrix of the DFT matrix. And we also scaled everything by square root of 2 to the power of n. So here, this introduced sort of a new new phase tensor, which is order 2, but basically it's we don't pass like the x1 value like horizontally. So this slides might contain like a lot of information. So it's but basically the idea is that if you sort of organize the phase tensor in this way, and if you combine the space of this x here into the sort of the Coulomb space of this matrix, and combine the values of y's into the row space of this matrix, these two are identical to each other. So it turns out this submatrix will arise when we try to extract Schmidt coefficients from the quantum for the QFT-Tn. See how we will introduce a few tensor identities associated with these phase tensors. So this is basically saying that this phase gates are actually unitary in the sort of diagonal direction, so this identity is basically the unitary property of the hardmark gates, and this property is the copy tensors are sort of isometric in arbitrary directions. And combining these two identities, we can sort of obtain the isometric condition of each horizontal rows of the QFT-Tn. So this allows to actually sort of manipulate the QFT-Tn in a certain way. So basically, if we want to extract the Schmidt coefficients at a certain card, so here I choose it in the middle. We're basically trying to calculate the singular values of this matrix by bending the wires of the upper division, so the upper partition and the lower division in different directions, and then we're sort of calculating the square root of the eigenvalues of this positive definite matrix here. And then because this upper part is the isometric due to this condition, we can actually drop like all the tensors in the upper partition. We only need to consider the lower partition of our system. And then by doing some sort of tensor simplification, so here the lower part, like all these H gates and control phase gates are unitaries, so they cancel each other. And then we sort of obtain this tensor network. And from the step to step 3, we basically use this identity arising from the definition of the order 4 phase tensor. So you can actually observe that this tensor matches our previous slides where we show that this tensor network is represents the top left submatrix of the discrete Fourier transform matrix. So in general, for a cut between qubit J and J+1, the Schmidt coefficient can be solely determined from the first J phase MPOs, and from the lower n-J phase tensors of those MPOs. So basically, if you have a cut here, we just consider this block, and it represents a certain submatrix of the DFT matrix. And for cut here, the Schmidt coefficient can be just determined from these tensors. And for cut here, it's these tensors, and so on and so forth. So to summarize, the Schmidt coefficients of the QFT at the cut between qubit J and J+1 are equivalent to the singular values of the 2 to the power of J times 2 to the n minus J top left submatrix of Fn, which we denote as Fn J. So as an equation, it's sort of like this. So Schmidt J is the Schmidt coefficient at cut J. So now we show some early results which prove that Fn J is approximately low rank. To do so, we consider the matrix arising from multiplying Fn J with its conjugate transpose. So there are a lot of math here, but what you only need to know is that eigenvalue equation can be sort of simplified to this form. So it turns out the exact same eigenvalue equation arises from the spectral concentration problem, which has been extensively studied in signal processing. So the original problem actually used the discrete time Fourier transform, but we use the discrete Fourier transform. So the difference is just that whether T is continuous or discrete. But for the spectral concentration, we're basically trying to solve the problem. So what input vector here? So this is like you can sort of discretize this into a vector. So what vector will have the maximum power in the frequency interval here when we do DFT relative to the entire interval? So you can sort of see like why the submatrix of DFT will arise, because we're actually specifying an interval instead of the entire region. So this is sort of like cutting the DFT matrix into a small submatrix.
Sorry, now you question what do you mean by power?
Yeah, okay, so power is sort of like just the area of the curve. It's actually you square the curve first and take the area of the curve. Yeah. So the DFT version of the spectral concentration aims to solve this equation, which we can see if we substitute n equals to 2 to the power of n and m prime to 2 to the power of j and 2w to 1 over 2 to the power of j, we can get an eigenvalue equation arising from the QFT Schmidt coefficients. So this eigenvalue equation has actually not been exactly solved yet. However, there are lots of results on the eigenvalues upper bound. So in particular, by slightly modifying results from this paper, we can get our main results here. So to summarize, the Schmidt coefficients of the QFT are solutions to a special case of the spectral concentration problem, whose upper bounds have been studied extensively. And the upper bound turns out to be independent of the number of qubits and partition of the system. So the intuition behind this eigenvalue decay is really just because this is a sort of a maximization problem. So basically by that, I mean, the first eigenvalue will sort of represent the maximum in the entire space under some constraints. And the second eigenvalue will be the maximum in the space orthogonal to the first eigenvector. And the third eigenvalue will be the maximum in the space orthogonal to the span of the first two eigenvectors. So we're sort of trying to push the eigenvalues as large as possible. So eventually the eigenvalue will sort of have a decay property. Okay. Now I will introduce like an interesting relation to the error law. So while the math may make sense, hopefully, it's not intuitive why the QFT circuits with these long-range gates and non-constant depths can have this small entanglement. So can we interpret the QFT as a physical process, which by that I mean a dynamics under some Hamiltonian, and understand low entanglement from there? So I will state what I mean by error law. So basically, so for Hamiltonian on one-dimensional lattice with interaction decaying faster than 1 over square root of r. So r is the distance between two sites. So this Hamiltonian will has a constant entangling rate. Basically, if we evolve an arbitrary 1D system with such Hamiltonian, the rate of change of the system's entanglement entropy will not increase with the system size. So the small entanglement of QFT seems to suggest QFT falls into this category. So can we actually solve the Hamiltonian for QFT to sort of like see this relationship? It turns out explicitly solving the Hamiltonian for QFT is very challenging because these H gates, hallmark gates, do not commute with the controlled phase gates. However, recall that we actually, through our analysis, that the Schmidt coefficient only depends on the phase gates. So actually, if we remove all the hallmark gates, the Schmidt coefficient will actually be invariant for any cut of the system. We can even show more that any bipartite entanglement measure will remain invariant from removing H gates. So that means we can actually just study the Hamiltonian for this circuit to sort of like to gain the same entanglement structure for the QFT's Hamiltonian too. And it turns out this Hamiltonian has exponentially decaying interaction, which is sort of like evident from like this exponentially decaying parameters. So you can see here is sort of evolving this Hamiltonian with exponentially decaying for a constant time. And this projector actually is just the Z interaction with scaled by like So it's sort of like, a pretty reasonable physical system. Therefore, to summarize, the QFT mask also has this underlying Hamiltonian with exponentially decaying interaction, although we didn't know how to solve it exactly. So this provides a more intuitive explanation of the QFT's low entanglement and is coherent with our analysis of the QFT's Schmidt coefficients. Okay. So I will then introduce the matrix product operator form of the QFT. So this will fall into sort of the more classical side where we try to simulate QFT using this low entanglement property. So the matrix product operator is a very useful tensor network structure. So a lot of efficient algorithms actually are based on it, such as the DMRG algorithm. The exponential decay of the QFT, of course, suggests that you can actually compress the QFT tensor network into a low bound dimension MPO. So I think probably a lot of you are already familiar with this, but just to indicate the notation I'm using, so you can sort of, so for matrix product operator, you can actually orthogonalize it into a specific form where we usually call it the canonical form. So here is basically it has an orthogonality center where all the tensors beside this orthogonality center will have this isometric property. So you can always orthogonalize a MPO using a series of singular value decompositions. So we want to find an algorithm to sort of compress the QFT TN into an MPO, which we will call the QFT MPO. So since the entire tensor network is consisted of several phase MPOs with trivial H gates sandwiched between, any MPO contraction algorithm will work. For example, the naive method, which we sort of contract pairwise first and then optimize the bond, or the density matrix methods. So these methods are stable but are relatively slow. We can also use the ZPUP algorithm, which is fast but maybe unstable. That means it may introduce like larger error compared to these methods. We can also use the fitting methods. They're not so slow, but may fail to converge in some cases. So for the QFT-TN, all these phase MPOs have their orthogonal centers of conveniently aligned at the loss sites. And the phase tensor actually have this special isometric property we sort of introduced. So this actually allows the ZPUP algorithm to be very stable. So it's actually a best candidate because in this case, it's both fast and stable. So I will just illustrate the algorithm using 4 qubits. So basically, we're doing a pairwise contraction of starting from the last site, which are the orthogonal centers of the MPOs. And we sort of like optimize the bonds sequentially through a series of singular value decompositions. And after contracting the first MPO, the orthogonal center will add the second site. And then we want to sort of like push the orthogonal center back to the last site by doing another series of singular value decompositions. And then we want to repeat the process until like we sort of contract everything into this form. So assuming we set the bound dimension of the QFT MPO to chi, the ZPUP algorithm will have a time complexity of approximately chi times n squared. So the constant is also very small. So for example, for 50 qubits, it only takes about 1 second to construct the MPO. And the truncation error will sort of like decay exponentially with the bound dimension you choose, and it scales linearly with the number of qubits. So these are some numerics on the errors. As one can see here, so for 8 qubit, for a bound dimension of 8, it's already sort of less than the machine precision. So it's essentially exact. So basically, for any number of qubits, we can sort of choose the bound dimension to be 8, and we can sort of have an exact representation of the QFT itself. Okay, so this fact actually allows us to sort of develop this the super fast Fourier transform. Applying the QFT MPO to a matrix star state is only depends on the input MPS bound dimension. So in general, it takes all chi times n time. So for exponentially expensive input MPS, the simulation is still exponential. For example, the state in Shor's algorithm where the Schmidt coefficient are actually uniform for the MPS states. But for an MPS with constant bond dimension, the simulation will only take time linear to the number of qubits. So how is this compared to the sort of gold standard fast Fourier transform? So it's unfair to assume the input as an MPS. Therefore, we must include the conversion time from a data vector of size n to the power of n, small n, into an MPS with small n size. So this will dominate the overall time complexity since the conversion cannot be faster than time linear to the number of qubits. So by using clever methods to turn the data vector into an MPS, such as randomized SVD or tensor chain cross, and combined with the QFT MPO, one can sort of turn the time of doing this classical Fourier transform into a spectrum of time complexities instead of a fixed complexity of fast Fourier transform. So it sort of depends on how compressible the data is. So if the data is very compressible, we actually sort of obtain the super fast Fourier transform. So again, we assume the data vector have length big N equals to 2 to the power of small n. So FFT is n in proportion to n log n, which is 2 to the power of small n times n small n, and the total time complexity of our framework basically by that I mean we do randomize SVD first, and then we apply the QFT MPO to it. The time is actually linear to the linearly dependent on the input MPS bond dimension, but it's still exponential to the 2 power of n, so it's not an exponential speedup. But as we can see here, for some regions, for example, if the bond dimension is constant, we gain sort of a linear speedup compared to the FFT. So for this region, we'll expect super fast Fourier transform. However, we can also use maybe even better method compared to randomized SVD. So we can sort of maybe push the boundary a little bit further. And that's, I think it's a very good research topic. So here are some benchmarks ran on the personal computer. So we take some examples such as one cosine function with some cusps, and we also try like 20 cosine one sine or like one sine function, and as one can see here, like it's a number of qubits equals to 18. We already see an advantage compared to the standard for fast Fourier transform algorithm. So this dashed lines represents the time, both including the conversion and the QFT MPO, and this solid lines represents the time of just applying the QFT, which means we assume the input to be MPS already. So this may be actually reasonable in some, I guess, condensed matter problems that, if your input, you are doing some maybe DMRG simulation first, then you already have an MPS, then applying the QFT, the Fourier transform on that state will be very easy. Okay, so I would like to conclude my talk with some discussions. So from the quantum information point of view, this small entanglement sort of suggests that this sort of bit reversed QFT might be a more natural definition for quantum Fourier transform, since the bit reversal operator introduced a lot of unnecessary entanglement. And also, an essentially decaying Hamiltonian for the QFT exists. So finding which will actually make the QFT much easier to implement on some quantum computers with access to long-range interactions, such as Rydberg atom quantum computers. Also, a lot of quantum operations do not actually introduce as much entanglement as they seem. So can we generalize this result to a broader class of operators? So I'm not an expert on quantum information yet, so maybe some of you may have more thoughts about what's the implication of this result. So I will hand it to you for more thoughts. And on the other hand, in the classical setting, an explicit formula for the QFT MPO might exist by sort of like our analysis, because the MPO form has a very structured tensors, and we might be able to write sort of like finite state machine construction of the MPO. But one major question we want to ask is whether that means we need to solve the spectral concentration exactly first, which people in signal processing have been trying for like 50 years already. So there are also broader implication, like can we make a general statement about what classes of functions or vectors can be compressed into a low bound dimension MPS? For example, maybe all smooth function can be expressed in low bound dimension MPS. And can we design better algorithms to convert the function or vector into MPS? So this will be very useful even outside of this super fast Fourier transform thing, because it will be it will allow like a lot of more tasks to be done in the tensor network settings. I will hand to the tensor network researchers for more implication. I'm just hoping this piece of information will be useful for people in this field. With that, that's I want to talk about, and I'm happy to take any questions.
Chris, there's a question in the chat,
Oh, okay.
Which says, why considering a reversed order of the qubit decomposition into bit strings changes the amount of entanglement of the quantum Fourier transform?
Yeah, so
can you just also repeat the question?
Yeah, so the question is why considering the reverse order of the qubit decomposition into bit strings changes the amount of entanglement of the QFT. So so from the intuitive side, it's like if you remove the bit reversal constraint, you sort of have that exponentially decaying Hamiltonian thing. And if you the bit of reversal operator has intrinsic like maximal entanglement. So it's like so I don't think I'm not sure if there's like very intuitive answer to this question, because it's just like the mathematical analysis of the submatrix of Fourier transform will sort of coming from the bit reversed QFT. Yeah, because
That implies there's something not fundamental about this property. Like the algorithm is achieved either way, right?
Yeah.
Like then the entanglement is very detailed about how you organize your gates, sort of in a sense. That's not like any transform has this entanglement inherently. It's how you design your operators in pieces that determines it. Is that implication of that?
Yes, kind of, yeah. Yeah.
I have a very particular question. Can you go back to the equations for the eigenvalue problem?
Yes. Yeah. This here.
Yeah, this fellow.
Mhm.
So this, I mean, I just saw that and it looked like some sort of problem you might see in interval systems.
Yeah.
Like the TVA equations or something like that. Is this all related?
Yeah. So I think this equation is actually like arise a lot in different problems, because it's really just a product of two submatrix of Fourier transform. So whenever you consider like you sort of like want to Fourier transform and then you sort of cut the sort of like the system in some way, you sort of have this equation arising.
But there's no like ansatz or anything like this you can use to solve these.
Oh, so I think people don't have like explicit formula for the eigenvectors of this function, but people call it like discrete prolate spherical sequences or something like that. So you can sort of generate them using some algorithm, but you don't have a closed form formula for them. Yeah. Yes.
Do you have a sense of how sharp this inequality is? Like I assume with numerical, you can kind of actually solve the eigenvalues for small cases. And
Yeah.
You have a sense that this could be strengthened a lot or it's pretty sharp already?
So sorry, what do you mean by sharp? Is
like if you actually calculate the actual eigenvalues for small cases, is this inequality like pretty close, or is there possibly like some massive strengthening available that we don't have theoretical access to?
so for small cases, it's like for example, for the extreme case, like if you just have n equals to sort of like 2, I guess it's so it only has like one eigenvalue, so it's like just I think so. It's like sorry, I don't think I do, like quite understand exactly what your question is.
You're talking about the inequality at the bottom of the
Here.
Yeah.
Oh, I see. Yeah. So basically, if you so for large n, this sort of like upper bound will be tighter, but if for small n, it will be the eigenvalue will be like very sharp. I think. Yeah. I think I'll answer. Okay. Yeah.
Do you have any idea if this applies to high dimensional Fourier transforms? Again, high dimensions. Is it we likely to also have this sort of effect, or is it totally different beast?
You mean like quantum Fourier
Like a
transform?
2D Fourier transform.
2D Fourier transform.
Yeah.
Yeah. I see. Yeah, I think you can sort of do like similar and analyze like here. You sort of like so I'm not exactly sure like how 2D Fourier transform, the circuit for 2D Fourier transform is, but you can probably see that the Schmidt coefficient sort of just come from this like a subset of all the gates, and those gates will form like a submatrix of quantum for like this coefficient. So I would imagine that this property might hold for higher dimensional systems, although like the decay might be can be slower. Yeah. Yeah.
Might be a stupid question, but like, while making an analogy to area law Hamiltonian, you cancel out unmarked operators.
Yes.
What's the reason?
Uh.
I think you just delete
those. So you mean what? Like, why can we remove all the Hartman gates? So they're like, so the first reason is like if you look at the previous like, so here you can see like the Schmidt coefficient only depends on these phase gates. So if you remove all the H gates, you actually get the exact same coefficient for the entire QF, like the circuit too. So that means the H gate actually do not, so it sort of rotate the base in a very complete way. Yeah, but it's yeah. So in general, if you sandwich like multi-qubit gates with one single qubit gate, it will change the entanglement structure a lot. But the QFT has this special structure which H gate actually don't affect the entanglement structure.
Oh, it's just they're rotating in a single side, so it's like the entanglement is this.
Yeah.
Operator is the same. Okay, I think I got it.
Yeah. Yeah.
So I have a kind of a naive question, thinking about Shor's algorithm and the quantum Fourier transform is part of that. Is there right, but then there's this beginning step where you have to encode your problem. Is there any, I don't really know much about that first step, but is there any sense in which for some primes you can encode it as an MPS, like an example where, and then you can do the MPO?
Yes, I believe so. So for Shor's algorithm, the MPS state before the quantum Fourier transform has the bond dimension in proportion to the order, like the period you're trying to find. So if like the period you're trying to find is small, you can sort of dequantize those cases. But the problem with Shor's algorithm is that the states, so the states before QFT has uniform Schmidt coefficients. So the only time we can sort of dequantize them is when the bond dimension is actually small. So we cannot do like approximations of those MPS. Yeah.
Why is the reason that you do not compress the input state from the first algorithm? Is it because you have uniform coefficients?
Yeah, it's Yeah, so I guess in terms of like maybe entanglement entropy, it has maximal entanglement entropy. It's just so it's like the number of like Schmidt coefficients. So the number of Schmidt coefficients are the period you're trying to find, but they are all uniform. So they don't have like any decay. So you cannot truncate them at some point, like without introducing too much error. So even if you just want to truncate one of them, you will introduce a lot of error already. Yeah.
So on one of the last slides, when you show the timings for the superfast Fourier transform, does this include the time it takes to load the data into an MPS or?
Yes.
Or not?
Let me. You mean this plot here or?
Yeah.
Right. So so this plot include both cases. So this dashed lines is the time for doing both conversion and loading the data and like doing QFT. And these solid lines are like the time without loading the data. Yeah.
You know why RAM data is so much worse than the fast Fourier transform? It's just the cost of loading it.
Yeah. So right. That's so if you look at the time complexity here. So for random data, you usually expect like maximum entanglement. So you actually has like worse scaling than for fast Fourier transform. Yeah. So this is like the line where both algorithms match, and like after this region, like this method will be worse. Yeah.
Thinking of applications, I mean, you may not want to apply the Fourier transform with some random data.
Yeah, that's true. Yeah. Yeah.
Do you think that generalizes if you do, say, 2D QFT into a low entanglement projected entangled pair operator? If you don't do the reordering?
Oh.
Or does do the cancellations not work out?
You mean for like 2D?
Yeah,
Okay.
if you do 2D QFT and use people.
So like sorry, like for 2D like if you have to
you encode your state in PEPs.
Yes, okay.
And you use a projected entangled pair operator.
Yes.
The QFT operator.
Okay. So for that you like do you still you ask to still
Is it still low? Would you expect it to be still low?
Yeah.
Have you thought about that?
I don't know. I think Ivan also asked about this, but I don't have a good answer because I think we need to sort of look at how the sort of circuit in 2D is. But I will expect it has like similar property to this. Yeah, so I think that's worth looking into. Yes, yeah.
The one comment there is that an interesting thing about the way these functions are encoded at the express is that when you actually encode a 2D function, in contrast to the 1D functions that you showed the examples for, it doesn't make a PEPs like a 2D tensor network. It actually just makes an MPS, but now where every tensor has two indices. So you're actually still rather close to the technology of maybe products, but it's still
But that messes up the QFT operator.
Yeah, how to do the QFT in that format is still something you actually can find. But just to say you don't have to immediately go to PEPs to do the 2D, so it's not very far off from what this would be about.
Okay. Thanks, Miles.
All right, let's thank Chris.
Thank you.